Can you hear me all right? Thumbs up in the back. All right, so I'm Dag Evensberget, and I'm a postdoc. Can you still hear me?
You might want to tilt it a little bit.
Yeah. Maybe I'll just hold it in my hand. Right, let's go like this. And I'm a postdoctoral researcher. Maybe you can put it on. Thank you. Cool. Researcher at Leiden University, and I'm very excited to be here today to be able to talk to you about how we can reproduce certain features of spin down in solar type stars with numerical simulations and observationally derived magnetic maps. This work is already published, Evensberget and Vidotto, and on this slide is also some of my other collaborators. So as we all know here, solar type stars spin down as they age. So they leave the contractive phase with a range of rotational periods here. However, by an age of approximately 600 million years, they all rotate in lockstep, sort of Skumanich rotation, where the period of rotation is proportional to the square root of the age. We can fit so-called gyro tracks or rotational history curves to this distribution. So here we have a rapidly rotating star that formed with a large amount of rotation, and a slow rotating star down here. And as time passes, they essentially converge onto this single track here. So we have essentially, this is represented by a broken power law, where the spin down time scale is constant in the top half of the diagram. And it's inversely proportional to the square of the rotation rate in the bottom half of the diagram. If we sort of turn this diagram in our heads, the nature of the broken power law is more evident. So essentially the fast star forms with more rotation. The slow star might start over here, but as they proceed towards the goal, towards the age of the sun, well, they kind of catch up with one another. So we don't know, for example, if our own sun was a rapid rotator or a slow rotator when it was younger. So now let's talk about a beautiful data set, the two-piece data set, where we have a bunch of solar type stars with known ages. So because these are cluster stars, the ages are pretty well known. And we got a good spread, for example, around this age here. And it's pretty well, it covers this pre-Skumanich spin down era, as I called it here on the left side of the diagram. It's pretty good coverage, perhaps, of this region. So of course, the two-piece data set doesn't just contain rotation, mass, and radius data. It also contains polarized spectra, which we can use to produce surface magnetic maps. This work has already been done by Colin Folsom and collaborators. And here I'm just showing the magnetic maps from that project. So you have the oldest stars in the sample here on the left, and then you get younger stars moving to the right and down. And you can probably see that the older stars have weaker magnetic fields, like less strong colors in this. And there's also a general trend that there's more detail for younger, more rapidly rotating stars. So now, can we reproduce the saturated and the unsaturated regime of spin down with these magnetic maps and a numerical model? Well, let's see. We use 3D wind modeling, and from the 3D wind models, we can calculate an instantaneous wind torque. For this, we use Batsaras Awesome, which many people have talked about, at least in the splinters already. It's a three-dimensional numerical code where the corona is heated by alpha wave energy. Here I'm showing a typical structure of the corona from a steady state from such a model. And we see a similar structure with a region of fast wind and a region of slow wind. This two-lobe structure is the alpha surface. Now, for the whole sample, we see that although there's a lot of variation in terms of the magnetic maps, there's essentially only one type of structure here. It's the two-lobe, sort of large-scale dipolar structure with a variety of inclinations. So recalling this fast and slow gyro tracks and broken power law fit, if we now show the surface magnetic flux, which is essentially an input to our model. Here, this is just the radial field multiplied by the area of the star, right? So there's kind of evidence of a saturated regime and an unsaturated regime, if you squint at it just right. And you see in the saturated regime, fitting like a broken power law, there's a different slope varying by about a factor of 1 between the two regimes. Now, what we find is that when we run our numerical models, this broken power law in the magnetic field sort of is carried through the model. So now looking at the wind mass loss, essentially here we have an almost constant level of mass loss for the rapidly rotating saturated stars. And then we have a drop-off for the stars that are in the unsaturated regime. The wind mass loss, of course, is important when computing the wind angular momentum loss, as you can see here. Once again, different slopes, a factor of 1 and a factor of about 3. So yeah, the difference is a factor of 2. And this is kind of a hint of what's to come. And now we obtained the wind torques. So in order to also try and calculate the instantaneous spin down rates, we need one more component. We need an interior model so that we can get the rotational inertia of these stars. And when we have the instantaneous torque and the rotational inertia, that gives us an estimate of the spin down time scale. Yeah, this one again. And now drawing on top of this, okay, so these are the wind-derived spin down rates as we compute them from our model. There's actually a pretty good match here. Oh, sorry, these are the wrong. Okay, let's skip this slide. Oh. Okay, so there was a little problem here. So these are the numbers I was intending to show. I must have messed up. This one I was plotting, sorry. So we see in like the fitted line to our data points here, shown in black, is perhaps serendipitously, it's very close to like this gyro tracks that we came up with originally. So yeah, you have the instantaneous spin down rate computed from the numerical models in black, very close here. I mean, they almost look flat. And similarly, we get the Skumanich spin down in the unsaturated regime. So what I was going to show before is just that initially we still have this pattern. These are the values that they come out of the simulation. But there is like an absolute offset of a factor of about 7. So if we scale the data points if we scale the torque or the moment of inertia, if you will, by a factor of 7, then we get it's like relatively good agreement. And looking again at like turning the diagram back in our head so that we have stellar age now on this axis and the spin down time scale, the period of rotation here. And these little tails that I've drawn onto each of the data points, they are the sort of instantaneous spin down rates that you would have based on the background field here again, which is based on that gyro track relation, so the broken power law, where we have either constant spin down time scale or the Skumanich spin down. And if I now put we draw the arrows which are calculated from the wind torques and the wind rotational inertia. Also here, there's kind of a good match. At least we see how in this region we see that slow rotators essentially have like a much lower instantaneous rate of spin down than these fast rotators. So now we may feel that I'm kind of a bit starved for data here. There's only really a few data points that I had in the saturated regime, but I just want to say that this saturation, it's not something that we just see in the two-piece data set for the ZEI. This is also, for example, here the data from Wright et al. There's a similar saturation, so you have a trend here that it does not continue. This is work that my master's student Tobias Eikelenboom has carried out, so please look out for that paper. However, in this case, to match the absolute values, we have to apply a scaling factor of 10,000 rather than 7, but the shape somehow still comes out. So yeah, that's kind of my conclusions. So to say it one more time, so what we see is that we reproduce the shape of the the distribution of rotations as a function of the age. And what we have is that the magnetic saturation observed with ZEI carries through the numerical model into a saturation of the mass loss. And of course, the mass loss is an important factor in computation of the angular momentum loss. So this also limits the angular momentum loss. And yeah, that's like the mechanism behind this. And to get the absolute values as well, we have to apply a scaling factor of 7. Thanks.
University of Michigan. So, okay.
Oh,
Yeah, so there's a very striking result that you have this magic number of a period of 3 days, time I think of about 600 million years. Perhaps you said something at the beginning, but can you give us a little more physical insight of where does that particular number of 3 days of the period come from? Why 3 days, etc. I mean, what physics gives us that?
right. So yeah, I can do that. I think, yeah, breathe. Okay, so the question is, how do I find essentially the saturation value of all this? Is this the question? The saturation value?
How you find data or what?
Oh, I don't know. No, that's this is like we are just we fit the numerical models to the observations we see, but the thing is like the magnetic field strength from the Zeeman Doppler imaging is an input to our model. So in some sense, the saturation is already present in the input, and what sort of happens here is that it just carries through the numerical modeling and results in like this difference in the spin down time scale. So, and yeah, the saturation value was chosen so that the gyro tracks that I show on some other slides. Right, let's do this by hand. I'll try like this. Right, so it's basically chosen so that these curves and the background vector field of gray arrows matches closely to the gray band, which is from the Gallet and Bouvier data, right? So there's I don't have like a physical explanation.
One more question. It's a very quick answer.
Now, what do you think? How a linear zero would fill the same factor 7 gap?
So the question is, do I have any idea on how to fill or how to get from the factor? So the missing factor of 7, do I have any idea where that would come from, right? Just show the slide. Okay, so here we are. We were thinking about core envelope decoupling, but the core envelope would have to sort of stay decoupled for the whole time with essentially no communication. So that was a bit confusing. So then is it like the SEDI's inability to resolve the small scale magnetic field? Maybe. Sorry about that. Yeah, or CMEs, it could be. But no, I don't have an answer, but there are many candidates, and yeah, it will also be interesting to have some data in other areas of the diagram.
Okay, let's thank Dag again. Speakers, Stefan of the Lot. Observatory, I think.
Is here fine?